Okay, so we'll continue on now with looking at the oxidation state 3 functional groups, which are primarily carboxylic acid derivatives except for the nitrile, but that's a functional equivalent. So we're going to look at how basically you can make all these things starting from a carboxylic acid. And then from each of those, what can you do with them? And so ultimately that will get us into the next module, which is, again, looking at the chemistry of the alpha carbon, specifically the acidity of the CH bond to do functionalization there. So in this very crudely drawn starburst, the carboxylic acid is really the key functional group. And remember that because the carbonyl is at the end, it's an acid. You have all this other stuff over here in terms of the chain. So whatever that stuff is, we're mainly just focused on that carbon. So as we see in red, those are the chemical shifts of the C13 of the carbon for the carbonyl. And then in green is about the relative location of the CO double bond stretch in the IR. So there's a little nuance to those as the functional group transformations happen. We'll look at a couple different transformations today and go through the nomenclature, a little bit more of the spectroscopic signatures. But mainly we're starting from an acid. And as I said, this heteroatom part is what we're really substituting. So one of the main things is, since acids are readily available, we can convert them into acid chlorides, which are really the most versatile of these for substitution. So the reason for that will explain the nature of what this X group is. So OHCl or amide, ester, whatever. So we're going to learn some more reactions that allow us to access these things. And as you can see, once you're sort of in this area, you can move back and forth from these different functional groups. So we'll start with the acid itself. And so that has, this line designation where really we're focused on that, and then R1 is whatever is along the chain at the alpha carbon. So once you identify the longest carbon chain bearing the acid group, you drop the E and then add OIC in the word acid for the nomenclature. And I've listed the first linear ones in terms of the sort of saturated side chain, and then one aromatic carboxylic acid. The main thing to note here is you see their boiling points are all pretty high, and that's due to the hydrogen bond donating and accepting ability of the OH group and the accepting ability of the carbonyl. So these things have a lot of non-covalent interactions that the molecules like to hang around each other, and that affects the physical properties. You see benzoic acid, that one is pretty high when you compare sort of the molecular weights. So when you go from that aliphatic side chain, which is kind of sp3 hybridized carbons, up into an aromatic ring, what it's telling you is the ring has other interactions that affect the physical properties quite a bit. That's mainly due to this concept of pi-pi stacking, a non-covalent interaction, which we'll see later on in DNA. So our normal sort of carbonyl bond dipole, now we have this acidic hydrogen. Remember, the pKa of a carboxylic acid is about 5. Because they all have this, that number can change based on what this R1 group is. So what makes these have such high boiling points is they can form these like dimer structures. Or you can imagine, two of these coming together, and then with the dashed line, you have these hydrogen bond donating, accepting things happening. And all of those weak non-covalent interactions add up to quite a bit. And another thing with this hydrogen bond donating, accepting scenario explains why the OH looks very different from alcohols. And we'll see that in the IR. So if you had a similar molecular weight alcohol, the acid is most likely always going to have a higher boiling point because there's more of these interactions. So IR, it's pretty easy to tell if you have the acid in there because the carbonyl stretch will be accompanied by the alcohol OH stretch that looks very unique. Carbon, you'll have that sp2 hybridized carbon in that region. Mass spec and proton themselves are a little bit more difficult because you don't necessarily always see the H of the OH in a carboxylic acid. So here we have the 4-carbon, this spectrum from Sigma Aldrich calls it butyric acid or butanoic acid. And the carbonyl stretch is pretty evident in region 3. And then we have that broad hydrogen bond OH stretching here, which looks very different from the alcohol. So again, through interpreting these different regions, you can zero in on what functional groups are there, and then definitely what functional groups are not there. So I want to review a couple ways of making acids. And one way that you can make an acid is using carbon dioxide, so CO2. And so if you expand out that CO2 into a Lewis dot structure, you'll be able to determine the hybridization, the oxidation state. You assign electronegativity, then you can figure out what type of reactivity it has. So we have a centrally bonded carbon, and there's 2 oxygens. So we need to make carbon into the octet. So that means we have to put a pi bond to each oxygen. So we have sigma, sigma, pi, and pi. That makes the carbon sp hybridized. The oxidation state, there's 2 oxygens. Each has 2 bonds, so it's going to be 4. And due to electronegativity differences, the carbon is going to be delta plus, so it's an electrophile. So for this one, C would be the correct choice. So the acid oxidation state is 3. Carbon dioxide has an oxidation state of 4. The carbon's electrophilic. That means we can use CO2 as a reagent with a nucleophile to attack that carbon, which will break a CO pi bond. That then changes the hybridization, reduces the carbon oxidation state, and allows us to make carboxylic acids. So because it has that sp hybridization, the molecular geometry of CO2 is linear. So we've seen a couple ways of doing this already, but I'll show you this first one here. As a review. So if we have a Grignard reagent, so it's organometallic, meaning there's a carbon anion plus a magnesium cation, that's nucleophilic. It can trap CO2, which is electrophilic. And then we adjust the pH and we can get a carboxylic acid. So for example, if we started with bromobenzene, the CBr bond is polarized that way, but we can treat that with elemental magnesium in THF, which is the solvent. The magnesium will insert into the carbon and bromine bond. And so that was a Grignard reagent. So the reactivity is equivalent. To this, where that carbon is now negative. So it started delta positive, it's now negative, so it's a nucleophile. So we can generate that. We can then bubble in CO2 gas. So that's a nucleophilic addition. And it makes this intermediate that we can protonate when we add acid to it. And so that really is a nice strategy that we can make any carboxylic acid from CO2 plus an appropriate Grignard reagent. And then once we've made that, we can take the acid into any other OS3 group acid chloride, amide, ester, anhydride, whatever we want to make. So the other two reactions, I'll kind of demonstrate the difference between using CO2 and then using cyanide. And then we saw prior with the Strecker reagent, a reaction, how to make a cyanohydrin, where the nitrile is equivalent to an acid in the oxidation state. So when I say retrosynthesis, that means we have some target molecule, and we need to think of a way of making that. So for the benzoic acid, we could make that by having the phenyl magnesium bromide Grignard attacking CO2. And the reason that works is because that carbon is delta plus and the oxygens are delta minus. Below it says nitriles are acid functional group equivalents. So those carbons in benzoic acid and benzonitrile are both oxidation state 3. A nitrile can be hydrolyzed into an acid. So functional group transformation. However, if our target molecule was benzonitrile, we could not use the same strategy as above. So the Grignard carbon is negative. Potassium cyanide, which is a reagent we've seen, that carbon is also negative. The big picture of this is CO2 and CN are both a source of one carbon atom. One is electrophilic and one is nucleophilic. So depending on what we're trying to make, we can either do the straightforward thing where we use CO2, or if we can't make the polarities of the atoms match, we're going to have to make a nitrile first and then hydrolyze it into an acid. So as we progress through these slides, we'll see how that is relevant. But suffice to say, no matter what the carboxylic acid is, we can either make it with CO2 or CN. So other reagents that we've seen to make carboxylic acids, primary alcohols using the Jones reagent. So that was chromic acid. That takes a primary alcohol from oxidation state 1 to 3. Another reagent was potassium permanganate. And then, as we saw last time, an aldehyde with MCPB8 as the Baeyer-Villiger. So in that case, the aldehyde proton migrates, that gives us the acid. So we have a couple different ways of making acids. Another way of doing it say we have an alkene where at least one of the sp2 hybridized carbons has an H bonded to it, so that's important. And then we're going to use ozone gas, and then this says oxidative workup. So typically what that means is we have some peroxide, so like hydrogen peroxide. What that will do is cleave the alkene, and then each carbon of the alkene gets oxidized up to the acid. So since that alkene was symmetric, we would end up with 2 equivalents of the same acid. So what you want to start thinking about in terms of piecing things together is, how did we learn how to make alkenes? That was from the Wittig reaction, where we took an aldehyde or a ketone, condensed it with that ylide. That can make an alkene. Ozone can then cleave that to make acids. And then we'll learn some transformations where the OH group gets substituted for some other heteroatom. So that OS3 functional group, whatever the X is, can be substituted. The mechanism by which this happens is called nucleophilic acyl substitution, or NAS. And all it is 2 steps that you've seen before. The addition of a nucleophile to the carbonyl group. And what is new now is an elimination of the existing X group. So it's substituted for something else. So we know that a nucleophile can attack a carbonyl carbon. It will break the CO pi bond. When that happens, the carbon changes hybridization from sp2 to sp3. And that's called a tetrahedral intermediate. The thing that's different now That X group is a heteroatom. So that tetrahedral intermediate will actually collapse where the lone pair on oxygen comes back down to form the carbonyl, and the X group leaves. That's the elimination. So the result of that is you're going back to sp2 hybridized carbon, and then you've introduced some other heteroatom there, your nucleophile, and you're still retaining the oxidation state of 3. So X is substituted for your nucleophile. So of all these groups, there's really only 2 of them that behave the best in terms of this reactivity, and that's an acid halide and an anhydride. So why is that? The part that I highlighted in blue, that is the leaving group. So when you're doing the substitution, the group that leaves needs to be stable. So in the first case, an acid halide, Cl- is the leaving group. If we consider the conjugate acid of Cl-, it's HCl. And from the acid, we can find the pK, it's -7. When you do that for all these other OS3 functional groups, notice how the pKa changes. The leaving group for an anhydride is the carboxylate. Its pKa is 5. For an ester, the leaving group is an alkoxide. The conjugate acid is an alcohol. The pKa is 16. An amide has an amide or negative nitrogen leaving group. The conjugate acid has a pK of 38. So again, it's this balance of acid-base strength. So a weak base has a strong acid, low pKa. We can translate that as saying that leaving group is very stable. As opposed to the other end, the N-, that is a very weak acid. So the N- is not a good leaving group. So stated another way, if you have an amide, it's very difficult to substitute the amide part here for something else. So amides are pretty special, not only in organic chemistry and reactivity, but also in biomolecules, because amino acids are connected to one another through an amide bond. In that scenario in biochemistry, it's called a peptide bond. So if proteins, enzymes are made of amino acids, why has nature chosen the amide bond? Another way to calibrate that is, of all the carbonyl-containing functional groups, the amide is the only one where that stretch is less than 1700. And so can you think of which one of these responses best describes why that is? So amide bonds are resistant to substitution. And an explanation for that is the lone pair on nitrogen can be delocalized onto the oxygen. So now the CO pi bond has less double bond character, it's more single bond. And that CN bond is more double bond-like. So the reason the carbonyl falls below 1700 is it looks less like a normal carbonyl. And because this bond is now stronger, it is harder to substitute this N group, this amine group over here. So that's one of the reasons why we're able to exist on this planet and live so long, as amide bonds are harder to hydrolyze, which means just under normal conditions, our enzymes don't fall apart into other things. So the answer would be C. The lone pair of electrons on the amide nitrogen is delocalized onto oxygen. So before we get too far into all these different substitutions, we're going to start with some pretty classical reactions. The first one is the Fischer esterification. So we're going to take a carboxylic acid, and then we're going to make an ester out of it. So we'll see this name Fischer quite a bit moving forward. So he was a winner of the second Nobel Prize in chemistry for work related to elucidating the structure of carbohydrates and purines. And so those are subcomponents of DNA that we'll see as well. The reaction is run under strongly acidic conditions. And notice the presence of an alcohol. So in this case, ethanol. So for an ester, we have that acyl part to the left, and then we have this alcohol part to the right. So this is an ethyl ester. So in the nomenclature, we name the alcohol part first. So there's 2 carbons, so ethyl. Then in the acyl part, there's 3. So it's a propane derivative, so it becomes propanoate, ethyl propanoate. You can take virtually any carboxylic acid, any alcohol, mix them together under Fischer conditions to produce an ester. So low molecular weight esters tend to be volatile. And you may have done one of these in lab, where you make an ester and it smells like some fruit, so it's typically apples or bananas or something like that. So we'll draw the mechanism on the next slide where we show how this happens. And to preview that, this oxygen is the oxygen that is incorporated into the ester, meaning that your existing OH must leave. So knowing what we know about acid-base chemistry, we'll walk through this where we show the intermediates that are either neutral or positively charged, and how we can affect the product yield from this. So we'll only focus on the acid-base proton transfers that are productive in moving the reaction forward, but keep in mind, you have other oxygen lone pairs in here that can be protonated or deprotonated, but we're only going to look at the stuff that moves us forward. So even though we have a carboxylic acid with a pK of 5, we're also in the presence of sulfuric acid that has a negative pKa. So we're going to use the carboxylic acid as a base that gets protonated by the sulfuric acid. And so that activates that carbonyl. And a resonance form will put the plus charge on the carbon. So now the alcohol can be a nucleophile. That will attack that carbon. So there's two things here. We have to remove this hydrogen that came from the alcohol. We have to get rid of the OH group, but we can't just make an OH group leave now because it'll have a negative charge, hydroxide. We're in the presence of a strong acid. So we'll show those two things stepwise. We're going to remove that. So that regenerates our acid, HA, sulfuric acid. And as I said, you have these oxygens, they all have lone pairs. I'm only going to show the one that's productive. We need to protonate one of those OH groups. So what that allows us to do is now an elimination where we reform the carbonyl and then water leaves. So we'll collapse to form a carbonyl. That water can leave. And then we just use the conjugate base to do a proton transfer. And that will give us our product, ethyl propanoate. So you notice these arrows that I drew between each intermediate here are these equilibrium ones. That means if you started with an ester and you had a lot of water in there with a little bit of acid, you could reverse this back to an acid. So depending on the concentrations of things, you can affect the equilibrium. A common method of increasing the product yield with the Fischer is you remove water as it's formed. That typically means it's being distilled out. And you have to judge based on the boiling point of the acid versus the water if that's feasible. But since a lot of these carboxylic acids have really high boiling points, they'll kind of remain in the flask and the water will be boiled out. So as that gets removed, it forces the equilibrium to come forward through Le Chatelier's principle. So to recap, the Fischer esterification, the conditions are generally your carboxylic acid, your alcohol, and strongly acidic conditions. The kind of reversion of that, or the going the opposite way, is called saponification, where you start with an ester. You're now under basic conditions, so sodium hydroxide, water, and heat. You end up with an intermediate metal carboxylate. And then you adjust the pH to isolate your acid. So saponification has been, historically used by humans to make soap. So how that kind of all evolved is, if you take, if you've ever felt like animal fat, it's kind of greasy to begin with. You can, take those fats, hydrolyze or saponify. Saponify just means you're hydrolyzing under basic conditions. And then as you would adjust, the pH, you can turn fats into soap. So a mechanism for that now, because we're under basic conditions, we're going to use negatively charged oxygen intermediates or neutral ones. So with our carbonyl reactivity, we have a delta positive carbon. We have hydroxide bearing a negative charge. At this point, if we don't activate the carbonyl, it just gets attacked. So negative attacks there, we break the pi bond. We balance our formal charges. So what you see now is oxygen's negative. It's not going to be positive under these conditions. So our tetrahedral intermediate can collapse. So reform the pi bond. If you look now, we have a choice of what it can do. We can have this alcohol leave, or we can have hydroxide leave. That's what this reverse arrow means. If the hydroxide leaves, we just go back to the start. So we'll make the alcohol leave. So that makes the acid, but that has a pK of 5. The leaving group was this alkoxide. So that's a strong enough base to come deprotonate this. So the reaction will sit there until the pH of the medium is adjusted to about 4. Which will then reprotonate that O minus. Any questions? In general, we can't do substitutions of OH from acids directly because the leaving group is OH minus hydroxide. The pK of water, the conjugate acid, is 14, and that tells us that's not a good leaving group. So typically we take our carboxylic acids and we transform them into acid chlorides. And then from that acid chloride, we can start doing the substitutions we desire. So there's 2 common ways of doing that. One is with thionyl chloride, and the other one uses oxalochloride and a catalytic amount of DMF. So we'll show the conditions and mechanisms for that. But once we have the acid chloride made, any substitutions just follow that NAS mechanism. So here's a model acid, 3-methylbutanoic acid. So we have our OH and we're substituting that for Cl. And then the acid chloride is a better starting material to use for further substitutions. So thionyl chloride has this structure shown. You have a sulfur with a double bond to oxygen and then 2 sigma bonds to chlorine. The reactions themselves are pretty straightforward to run. You would basically just take your acid and run it in thionyl chloride as the reagent and the solvent. There's a downside to this because if you look at all the other stuff generated, so you have OH that's substituted for Cl. So a Cl comes from this, but what happens to the other atoms and elements in the thionyl chloride? So they produce byproducts that typically you have to neutralize or scrub based on their nature. So really what we're trying to do in this mechanism is transform this OH into something that can leave. So if we take a lone pair on oxygen, we can have it attack that sulfur. Even though it's a heteroatom, it has these 2 chlorines which are electronegative bonded to it. And I'm going to show this stepwise where we form an OS bond, we break an SO double bond. So there we've balanced our charges out. The acid oxygens plus, thionyl chloride oxygens minus. So that allows us to do an elimination of one of the chlorines. So at this point, we now have a chlorine nucleophile that can add to the carbon of the carbonyl. So we've balanced our charges. And now this OH we started with, all of this stuff is now a good leaving group. So it will collapse to form the pi bond. We break that sigma bond. That forms an acid chloride. We get this byproduct that's going to collapse and form HCl, and then SO2 gas. So that's driven by entropy, where one thing's become two things. And the reason these are kind of a pain to run is because now you're generating a strong acid and then SO2, which is a gas. It's these things will basically, if you have any sort of metal around, it'll corrode the metal pretty quick. So essentially what happens is the reaction vessel has to have a bubbler that traps these things and neutralizes them before they exit the apparatus. But the main thing here is, because the action's only happening where the acid is, as long as you don't have other stuff along the molecule that can interact with the SO2, it's pretty robust. Another way of doing that that's a little bit more mild uses oxalochloride, which is the reagent shown in the middle here. So by itself, it's an acid chloride, but notice it's kind of two acid chlorides in one. And then the reaction has to have this catalyst, DMF. So DMF is an amide. So overall, you would get the same acid chloride product out. One of the reasons to run this is oxalochloride is a little nicer to handle. It does have a smell to it, like you ever have to mow the lawn for your parents? Like if you mow the lawn and the grass is dry, there's kind of like a fresh cut grass smell. Imagine that, but a little bit more intense. And then the presence of this DMF, the DMF and the oxalochloride form an intermediate that when the reaction progresses, it produces carbon dioxide and carbon monoxide. So if you put a balloon over your reaction that's deflated, you'll know the reaction's occurring because that balloon will eventually expand. And so it'll get to a point where no more gas is evolved and you can be certain that it's complete. So let me run through some arrow pushing on how those two things form to the intermediate that reacts with the acid. So at the start of lecture, I said amides have resonance, where the nitrogen lone pair is pushed up onto the oxygen. that resonance form is important because now that oxygen is nucleophilic. So what it will do is react with a carbonyl carbon. So it forms this intermediate. So N plus, O minus, we've balanced the charge. That intermediate, because it's tetrahedral, will collapse. So reform this pi bond, Cl minus will leave. What happens next is that now we have a CN double bond. Remember I said like iminium ion? So this is an iminium ion. That chlorine will attack that carbon. So now there's no charges. This thing's going to collapse. We'll reform that CN pi bond. We're going to break that bond and now form a CO double bond. Now the weird thing here is that bond will break, but the electrons go on the carbon, which causes a chloride to leave. So here you're forming CO2, here you're forming CO, and then Cl minus. So this iminium ion balanced by the chlorine is the intermediate that reacts with the acid. CO2 and CO are bubbled off. Just like we saw with thionyl chloride, the carboxylic acid then attacks that. It forms an intermediate. That Cl minus will then displace, which regenerates the DMF, which was a catalyst. So I'll let you push those arrows so you can, get practice and how that happens. But it's another method to make an acid. It's a little bit more mild, it's easier to run, easier to observe the progress. So we know how to make the acids. We now have two ways to make acid chlorides. What are the spectral signatures? For an acid chloride, it always has to have carbonyl chlorine, regardless of what that R1 is. The signature in IR is that the carbonyl stretch is almost always at 1800. So when you're looking at your IR data and you see something at 1800, it most likely has an acid chloride. Because there's chlorine, the mass spec parent to parent plus 2 should show a 3-to-1 ratio. And then your proton and carbon, really what you're looking for is the carbonyl sp2 hybridized carbon in that region above 170. So we can see by this 2-carbon acid chloride, acetyl chloride. If you look right there, the tip of that peak is right at 1800. So regardless of whatever this group is, that carbonyl is almost always at 1800. So I think what we'll do is end a smidge early today. We have enough time on Monday to complete the rest of this stuff. I think this is a nice breaking point because what we've seen is now that we have the acid chloride, how do we substitute that chlorine for these other nucleophiles to make these other oxidation state 3 functional groups? And then what are their spectral signatures? And so that will wrap up this module on Monday. And really, again, the thing that you'll want to pay attention to is as you move through, those different oxidation states, how can you use the IR primarily to tell the difference between carbonyls, and then what conditions allow you to do that.